root locus, or when the angle of attack means the aircraft flies at a lower angle of attack. If the aircraft flies at a higher angle of attack, then both the case we have to try to sketch the root locus, then we have to investigate. While this is for complete root locus of a pitch orientation control system or higher angle of attack. This is nothing but your outer loop of your control system. For outer loop means then we have to take care your overall transfer function. This is where integrating gyro having a transfer function that the K is a gyro sensitivity divided by S, the transfer function for your integrating gyro. Then you have a inner loop plus as well as minus. Then your elevator servo transfer function minus 10 divided by S plus 10. Then your aircraft having a transfer function for aircraft dynamics, that is a transfer function of the aircraft is already specified. Then your pitch rate is output, that your theta dot is to be out, that will be compared with your rate gyro sensitivity, and also it will feed back to your integrating gyro command input. Okay, this is your complete block diagram of your pitch orientation control system. So now this here we have integrating gyro sensitivity. First I have to try to sketch my root locus where my integrating gyro sensitivity is here 0.527. If it is 0.527, then we first reduce this block diagram reduction techniques. You have to make a single block because it is a negative feedback control system. Therefore, your G of S to be your, that means your loop one transfer function can be calculated from G of S divided by 1 plus G of S into H of S. Now these two blocks used to be cascade block. While applying block diagram reduction techniques, you just multiple these two blocks, then I will make it as a single block. Then this your feedback is to be your rate gyro sensitive, that is having a value of 0.527. If it is 0.527, then we have to find out your inner loop transfer functions. That means the closed loop poles of your inner loop transfer function, that may be open loop for your given closed loop control system, overall systems. Okay, if it is a closed loop poles, we have to find out for this case, then it is a open loop for your outer loop cases. Okay, then how can you find out means we can use this formula G of S divide by 1 plus G of S into H of S. Then we make it as a this overall block into single block, where in this case your G of S nothing but minus 10 divided by S plus 10 into your aircraft dynamics transfer function. Your H of S to be your feedback, that is a rate gyro sensitive value is a 0.527. Then it will make a single block. Then we combine this K by S into this above equation. Then we will get your overall outer loop transfer function. Then you try to sketch a root locus. Okay, in this case here S1 indicates your closed loop poles from your previous case for your inner loop condition. For your rate gyro sensitive value is 0.527. There are two root locus cases is there. One is for capital S1 indicates this associated with your rate gyro sensitive value is 0.527. That another values for S2, the root locus branches are related to your rate gyro sensitive value is 0.23. Now while investigating these root locus branches, we see that while your rate gyro sensitive value is 0.527, where it is a rate gyro sensitive value of 0.23, that is a root locus branch is S2. So S2 is now in this location. When the rate gyro sensitive value is very low, my poles are far away from that origin, because S2 is a root locus branch of your where the rate gyro sensitive value is 0.23. Suppose if I am increasing my rate gyro sensitive value is 0.527, the poles is the S2 poles is try to move in your towards your left hand side of the S plane. That means the region of unstable region 2 will try to move in a stable region. Therefore, while increasing your right gyro sensitive, that will give a wider range value of your selecting your right gyro as a integrating gyro sensitive values. Here we see here in this bottom of the table, we mention where your right gyro sensitive value is a 0.23. That minimum allowable gain for your right gyro integrating gyro sensitive value is a 1.58 to 2.83. If I am increasing my right gyro sensitive value, it leads to choose wider value of your integrating gyro sensitive values. These things we have to observe from these root locus branches. So that's why we increasing your right gyro sensitive values, the overall control system performance, or it will leads to increase your integrating gyro sensitive values for your stable region. Suppose if the right gyro sensitive values very lower values means then these poles are far away from their your origin. Maybe these values less than 0.27 means these S2 to root locus branches now you shifted to your right hand side of the S plane. That is so far away the plane means then even though if you are selecting your right gyro sensitivity, integrating gyro sensitivity, the system becomes unstable condition only. So while increasing your right gyro sensitivity, it leads to your location of poles in the right hand side plane. It tends to try to move in a towards your left hand side of your S plane. If the poles are shifted from left hand side, right hand side of S plane to left hand side of S plane, then the system becomes stable. So we select your wider range value of your right gyro sensitive value. It will leads to or it will allows to select higher value of your integrating gyro sensitive values. This K value. Okay, this is where this root locus for your that means the complete pitch orientation control for higher angle of attack. The same way you have to choose for this is your pitch orientation control system for lower angle of attack. For one cases, that means S equal the closed loop holds from this 0.527. Another one is the closed loop holds from your 0.23. Okay, where it is 0.23, that means your 0.23 means this is your S2 root locus branches. So where it is a 0.23 means the root locus branch start from these poles. It will follow this path. It will cross the imaginary axis in this location. Right? If it is cross this location, in this location, what is the value of your right gyro sensitivity? Integrating gyro sensitivity. This is a limiting value of your integrating gyro sensitivity or maximum value of your integrating gyro sensitivity value for the system is to be stable. If this beyond this one, if this K, that the system becomes unstable. So in the same way, if you look at your S1 root locus branches where your right gyro sensitivity value is a 0.527. If it is a right gyro sensitivity 0.527, my root locus branches like this, it will towards move in this direction. It may be cross imaginary axis in this location. Therefore, in this location, your gain value may be higher value. So in this location, what is my higher values. So I'll compare these two cases. I have a wider choice of K. That means that I have a higher rate integrating gyro sensitivity values than I have higher value of right gyro sensitivity values. If you choose the gain of the right gyro sensitivity value higher value, then it will leads to or it will allow us to choose your higher value of integrating gyro sensitivity for the systems to be stable conditions. So we try to sketch the root locus for your outer loop. Then we check it out whether up to what range of the K value should be stable or unstable. You see here, in this case, this is your previous case for higher angle of attack, this were lower angle of attack. We have to find out up to what value of K the system is to be stable for both the case. Where the right gyro sensitivity values, if I am increasing my right gyro sensitivity values, Then up to what value you have to increase your integrating error sensitivity value, then we have to look up while sketching or while investigating your root locus studies. Okay. Then if you all here we are going to only discuss with your all performance oriented of your control systems. If you not improve your gain value, how may the system will be stable, or how the stability of the system will be affected, then only we are, then these are the things only we are going to discuss these entire subjects. Okay. Up to what range value of gain my control having, then based on that how my stability of the system will be changed, that things only we are going to discuss. So here sophisticate up to what range of gain the system is to be stable. So here I would like to discuss one cases, and you try to sketch root locus for remaining cases by using MATLAB. Okay. So in this case I have a transfer function for, I have to take a lower angle of attack. So the transfer function is minus 15 s plus 0.4 divided by s square plus 0.9 s plus 8. This is my aircraft transfer function. Then my elevator transfer function is minus 10 divided by s plus 10. We have to select your rate gyro sensitivity values. I have to select two different rate gyro sensitivity values. One is 0.527, another one is 0.23. I try to sketch, or otherwise initially we say to your rate gyro sensitivity values 1. Then while sketching a root locus, then you have to find out up to what value of these rate gyro sensitivity 0.527, what is my damping. That things we are going to discuss today lecture. So I have a transfer function like this. First things you have to consider, say, inner loop. That is your elevator transfer function. That elevator transfer function is to be minus 10 divided by s plus 10 then your aircraft transfer function minus 15 divided by s plus 0.4 divided by s square plus 0.9 s plus 8. This is your block diagram of this elevator, then your aircraft and aircraft dynamics, then your feedback to your gain value, rate gyro sensitivity. You put integrating gyro sensitivity, sorry, rate gyro sensitivity, RS. Initially we choose k value say 1, then we have to check when the k value is 0.527, when the k value is to be 0.23. Two different cases you have to check your root locus. Therefore my g of s to be combine these two cases. My g of s into, initially we assume the rate gyro sensitivity value is 1, then g of s to equal to minus the minus plus 150 into s plus 0.4 s plus 0.4 divide by s plus 10 into s square plus 0.9s plus 8. Okay. Then we are right here essentially. Initially we said 1. Then while varying this gain value, how my the stability of system will be changed, we can see in the root locus. Okay, then first thing is I have to step 1 is I have to locate my poles and zeros of your given loop transfer function. In this case, I have zeros is s equal to s plus 0.4 equal to 0, then s equal to minus 0.4. This is my 0 minus 0.4. This to be your zeros. Then my poles are poles. One is s plus 10, therefore s equal to minus 10. Then s square plus 0.9s plus 8 equal to 0. While solving this equation, what are my poles? And I get my poles s equal to minus 0.45 minus 0.45 plus 2.79 j omega plus 2.79 j omega. This is your real, sorry, one poles. Another one pole is minus 0.45 plus or minus, I use minus 2.79 j omega. That's why I mark poles are marked as a cross symbol. One pole is located at a minus 10 in this location. Another pole is located at minus 0.45. So here one zeros that is located at 0.4. 0.45 here. So almost this location 0.45, this 0.5. That is this location. I have two poles. One is 0.45. Then this to this height is 2.79 j omega. 2.79 j omega. Then is one is then minus 0.45 minus 2.79 omega. Therefore, this value is minus 2.79 j omega. Okay. Then once you locate your poles and zeros, then step number 2, we need to find out whether the real axis will be part of the root locus or not. Then we have to select some test point. So I have to select one test point here in the real axis. The right hand side of the test point, the sum of poles and zeros count is 0. Therefore, this portion will not be part of the root locus. Then again, I'm taking here one test point, T2. The right hand side of your test point, the total number of poles and zeros count. So here I have only 1 zeros, therefore the count is odd number. Therefore, this portion will be part of the root locus. That's why I mark this here. This portion will be part of the root locus. Okay, this portion will be part of the root locus. Okay, then I have to take another test point here, T3. The right hand side of the test point, the total number of poles and zeros count is, here I have 1 poles located at a minus 10. Then 1 zeros is at a located is minus 0.4. Therefore, the count is 2. It is a odd even number. Therefore, this portion will not be part of the root locus. Therefore, my root locus branches in the real axis is lies in between minus 10 to minus 0.4 in this real axis. Okay. Then we already told that. Okay. Then step number 3. Then we need to find out angle of asymptotes. Why we need to find out angle of asymptotes means all the root locus branches start from poles and it will meet at 0 at infinity. Suppose if we consider these root locus branches, maybe these root locus branches start from poles, it will move towards this direction, it will meet at zeros at s equal to minus 0.4. Okay, it is one root locus branches. The remaining two root locus branches start from poles and it is follow the path of asymptotes. It will meet at zeros at infinity because we don't have any zeros. I have 3 poles, but I have only 1 zeros. Maybe one root locus branch starts from poles, it will meet at zeros at s equal to minus 0.4. Then remaining 2 root locus branches start from poles and follow the path of asymptotes, it will meet at zeros at infinity. Then we need to find out asymptotes. I need to find 2 asymptotes because I have 3 root locus branches. Out of 3 root locus branches, 1 root locus branch start from poles at s equal to minus 10. Then it will towards moves the left hand side of the s plane. Then it will reach at zeros at s equal to minus 0.4. These root locus branches over. Then remaining I have pending root locus branches is 2 root locus branches. Then we need to find out 2 asymptotes. Therefore, the 2 asymptotes, that means your angle of asymptotes, angle of asymptotes. The formula is plus or minus 180 degree 2q plus 1 divided by n minus m, where q varies from 0 to up to n minus m. In this case, I have 3 poles, I have 1 zeros. Therefore, n minus m value is 3 minus 2. I will get q values varies from 0 to 2. If it is q equal to 0, what is my angle of asymptotes? My angle of asymptotes is equal to plus or minus, we will get 180 divided by 2, we will get plus or minus 90 degree. I need only 2 asymptotes. Therefore, I take one is plus 90 degree, another one is minus 90 degree. Then where I have to locate? That where the angle of asymptotes intersect with the real axis, that point is called as a centroid. C. Then we need to calculate centroid. Centroid is means sum of poles minus sum of zeros divided by n minus m. Sum of poles means what are the poles? One is minus 10, another pole is minus 0.5, plus 2.79 j omega, then another pole is minus 0.5, minus 2.79 j omega, minus plus will be cancelled. It is sum of poles minus sum of zeros, where your sum of zeros is minus 0.4, divide by n minus m. N is 3, m is 1, therefore n minus m value is 2. So sum of poles minus sum of zeros divided by n minus m. So here minus 10 minus 0.9 minus means a plus 0.4, then divide by 2, I will get minus 5.25. Therefore minus 5.25 this point. They say minus 5.25. This is your centroid. So in this point, you use your protector, you measure angle is plus 90 degree, another one is minus 90 degree. Where the plus 90 degree is a counterclockwise direction, minus 90 degree is a clockwise direction. So if you place your protector at this point, then this angle is 0 degree, then 10, 20, 30, 40, 50, 90. When it comes to 90, it is exactly vertical line. Therefore, I need to choose my asymptotes for plus 90 degree, then same way minus 90 degrees comes vertically downward direction. This is my angle of asymptotes. Okay. So maybe the root locus branches start from any angle from these poles, then it will follow the path of these asymptotes. Then I need to define up at which angle the root locus branches start, because it is a complex poles. If it is a complex poles, it will start a root locus branches at the angle of departure. Then we need to find out angle of departure. So next step I have to find out my angle of departure. Right. Then we need to find angle of departure. Space. Then we need to okay. Now can you find out your angle of departure? So here I wrote here angle of departure. Space. We can use departure. So here I have is my one pole is located here, then one pole is 0.410 is located here. Then here I have here one pole, the same I have here. Okay, so this is your complex pole. This pole I have to find out angle of departure. This pole I designate A. Then you draw a vector line from other poles to your complex poles, or at which pole we are going to find out angle of departure. So this pole I am going to find out angle of departure. Then I draw a one vector line. The same way I have to draw another vector line. Then I draw a vector line from the zeros. So here I have one zeros. So we need to find out this all this angle. So this angle, this to this line angle is a 90 degree. Then we need to find out this angle, this to this angle. I make it as a theta 1. So I always this pole theta 1. This theta 2. Theta 2 is a 90 degree, and it is make it as a theta 3. So angle of departure for a complex pole located A formula is 180 degree minus sum of angle contribute from other poles to a complex pole. Other pole is one is located minus 10, another one is located at this location. Therefore, we make angle is theta 1 plus this angle is theta 2. 180 minus theta 1 plus theta 2. Then plus sum of angle contributed from zeros. The zeros is contributed angle is a theta 3. Then we need to find out theta 1, theta 2 is a 90 degree. Then we need to find out theta 1. So from this point to this point used to be 10, because the distance is this to this distance is 10. But this to this distance is, because this is a 0.45 minus 0.45 minus 0.45. If it is this a minus 0.45, that is a this means the distance is 0.45. If it is a 0.45, what about this distance? Then I make a triangle. If it is a 0.45, then it is the remaining value is a 10 minus 0.45, that will say 9.55. So this distance is 9.55. The height is a pole's height, okay, because we already know that this value is a 2.79 j omega, right? 2.79, okay. Therefore, the height is 2.79. Then we need to find out this angle, theta 1. Therefore, use the tan theta 1 is equal to 2.79 divided by 9.55. Tan theta 1. 2.79 divided by 9.55. So 2.79 divided by 9.55. Then I'll get 16.285. So theta 1 angle is 16.28. Theta 1 is 16. Based on the screen is visible to all of you. Dear students, the screen is visible to all of you.
Yes, sir.
Okay. Just 5 minutes. I think you have a guest lecture also. So we find out theta 1. The same way you have to find out theta 2 is a 90 degree. Then we need to find out theta 3 also. Then theta 3 we make this a triangle. If you take this a small triangle, yes, we need to find out this my angle. Up to this angle is a theta 1, right? But this is this 0.45, this location is 0.4, then the gap is a 0.45, and this up to this distance is 0.4. Therefore, we get 0.5. That will get 0.05. This distance is 0.05. Again, the height is 2.79. Then I use the tan inverse of divide by 0.05.